So I'll share my screen again. So our first step is to get the MBAL software. So I'll go to program file. I think I have my petroleum expert there. Oh, is it? Okay, this is our petroleum expert. This is our petroleum expert. We go to it. We go to MBAL. This is MBAL here. We right click on it and we take create shortcut. And then we said yes. Then our MBAL is created on the desktop. Where is it? Am I getting blind? That's Prosper. Okay, this is our MBAL. That's our MBAL software. That's used for reservoir modeling and to predict the performance of reservoir under different energy conditions. So this is our MBAL software. We have up here, we have 4 aspects. We have file, we have tool, we have unit, and we have help. For every software, there's always a help button. There is always a help button. For every
For every
software,
software, we always have this help button that we can use to go through the software.
my sound system is disturbing, so I'm trying to walk through it. Okay, so I'll come to file. I will take on new. I want to start a new project. Now, when I go to tools, there are different aspects there on that MBAL that you can use. We have material balance analysis, we have reservoir allocation, we have Monte Carlo simulation to analyze the uncertainty of a reservoir and the probability of it to produce. Then, then we have the decline curve analysis. We have the 1D modeling. We have the decline curve analysis. We have the 1D modeling. We have our multi-layer analysis. We have time reservoir, and then we have streamline. I don't know. Can you hear me well?
No, sir.
Can you hear me well?
No, sir. No, sir.
Okay. So what we have here, we have our material balance analysis. reservoir allocation, Monte Carlo. We have decline curve, 1D model, multi-layer analysis, tight reservoir, and streamlines. So these are different aspects that we have inside MBAL that we can use to do our analysis. So we are going to start up with material balance. So we click on material balance. We did a material balance equation when we were looking at Excel for oil and gas. I took time to talk about the material balance equation, especially for oil reservoir, as complicated as it is. Then I also looked at some analysis. We did some calculations with Excel. So today we are going to see how we can use this MBAL to do a lot of analysis. So first thing, we have gone to our tool and we have chosen material balance. That's what we want to work with. We will work on material balance. We will do some 1D modeling. Then if we could have time, we will also do multi-layer and streamlines. We'll do multi-layer and streamlines also. But today we are working on material balance. So since we have taken material balance, we have a lot of aspects that have appeared up here. We go now to our options. The first thing in our option is to decide what we are working on. We have our reservoir fluid. What type of reservoir fluid are we working on? It could be oil, it could be gas, it could be retrograde, it could be general. General simply means that you have to define an equation of state, but we'll work with oil for now. How many reservoirs do you have? In this case, we are calling them tank. You may have 2 reservoirs, 3 reservoirs, but in this case, we have just a single tank. PVT modeling, we have simple PVT modeling. Then for production history, we have by tank. And then we have our compositional model. There is no compositional model. Once you take on compositional model, you see a lot of things that will come up that you need to start handling. We have, for example, if you take on tracking, you now see that this equation of state model has not come up. Equation of state. We are going to see how we can model our equation of state using PVTP, I think the week after next. So for now, we are working with simple or the black oil model. So our compositional model is none. I've already explained the difference between black oil model and compositional model. I've explained it so many times. So we can have our company information there. Then when we are done with that, we take done. So we have our tank 1 that is created there. That represents our reservoir. We will go now to our PVT data. We take fluid properties. We take fluid properties. Okay. Alright, so we put our PVT properties. What we have here is the formation gas oil ratio. We may have here maybe 500 stock standard cubic feet per stock tank barrel. We may have our oil gravity of 30 in API units. We have our gas gravity 0.76. We have our salinity. Most of these aspects we have already discussed about them. We may have 40,000. Then our contaminants, we may say we have no contaminants there. 000 000. All right. From there now, we are looking at our correlations. The same thing we did with Prosper. To correlate for BP, RS and BO, we use the Glasso, and to predict for oil viscosity, we have the BAL. But what we can also do is to do a matching, like what we did in Prosper. We have our matching. So we'll come to match. They have now asked us to input our table, here. So I'll just copy my PVT data from here. I hope it's going to enter well. So let me see. Okay, I don't have a single Excel for that, but this one is not just like Prosper where it could copy easily. Most of the time the MBAL refuses to copy. I have my paste table there, it's refusing to go. Prosper will always just copy easily, but this MBAL, at times he will copy, at times he will not copy. So we have only some parameters coming in. Okay, but we have to do our match because we can't work without the history match, the PVT matching. I need us to do the match. So I'm a little bit slowed down by this. Okay, let me take this data. Transformation volume factor. Okay, the data actually is refusing to copy. So we don't have any choice than maybe if you want to do the match, you have to put it one after the other. You put all of these values for pressure, you put the one of gas oil ratio, we put the one of oil formation volume factor, oil viscosity, gas formation volume factor, if at all you have it, and then we have gas viscosity. And then we have to go now to match. When you go now to match, of course we cannot go there because we don't have any data. Once you go to match, you will now calculate. Then you have your parameters, you have your different parameters exactly like we saw in Prosper. You have your different parameters, you start comparing to see which one is a better option. If you don't want to do the match, you can also input a table value. There, and then you ask the software to use tables. Because if you look at what we have here, we have use tables, we have use matching, we have use table, and we have use matching. So since the data does not want to copy, I don't think we'll have time to do all copying one after the other. If some few could copy, would have at least worked on it. So just one value copying. I don't have a single file for it, so if I go and browse and select, it's going to be an issue. Alright, so what we'll do is we'll follow the same process. I'll send the data. We don't have time to do the matching, but there's no issue with that. So what I will do is I'll send you the data and you try to do the matching. You try to do the PVT matching here. Once you do the PVT matching, this point here is going to highlight to show that you are using your matching for it. So I've already explained a lot about it under Prosper. So what we're supposed to do here is just to do a repetition of it and do a match, because we have also different reservoir properties that are changing with different PT conditions. So we have to get an equation that we can use to predict these properties at pressure and temperature conditions that we did not measure in the lab. So we have to do that PVT matching. So I'll send you the data, you come to matching, and then you input the data, and then you do your PVT matching. So that's okay. Our next thing now is to go to input. We want to put now the reservoir parameters. We want to put now the reservoir parameters. We'll go now to tank data. We'll go to tank data. So we are just going to give a name to this tank as a reservoir. We'll just give a name to it as reservoir, maybe reservoir 1. And then our temperature, let's say 160 degrees. Our initial reservoir pressure, let's say 3200. Our porosity 0. Let's say 0.24. Our connate water saturation, let's say 0.23. Our water compressibility, you can use correlations. If you have the value, you can use the value. If you have the value, you can easily use it, but if you don't have it, you can use correlation. Our gas cap, we may say no gas cap for now. Our original oil in place, we need to know the value of the original oil in place that have been calculated from volumetric analysis. Once you have calculated this from volumetric analysis, you can now input it here. What MBAL is doing now is refining that value to get a more concrete value. So what we'll just see here is, let's say 290 million of stock tank barrel. That's our original oil in place. Our production date, let's see the production data that I have here. Okay. Okay, we could use this. Our production starts from the 1st of January 1980. Start from the 1st of January 1980. That's the start of our production. Okay, we have now inputted the tank parameters. The next thing is to go to water influx. So we'll go to next. It now moves us to next. We know that generally the reservoir is either in the transient state. I've already explained the meaning of transient flow, or in the pseudo state condition. And in these situations, there is always that water influx into the reservoir. That means as you're doing production, water is gradually moving in to occupy the space that was occupied by the hydrocarbon or the oil that you have removed. So you may have a similar amount of water entering the reservoir to the amount of oil that is produced. So we generally have this water influx into the reservoir. So we are not going to say none. We are going to choose. There are so many models that can be used to get this, to understand how this particular influx is taking place. Various correlations. I think I have a book here which I will share with you. Reservoir Engineering Management, or Advanced Reservoir Engineering. any of them will have all of these, most of these correlations inside. So you have to take a good look at that so that you understand what each of them are saying. I may just take a glance at what I have here. Alright, this is a water influx model by Felkovich in 1971, and he is now explaining what is happening with the oil water contact as a result of this production taking place. So we see an equation that he developed in order to calculate the net water influx into the reservoir. So you have a simple equations like that. Then you can calculate the average reservoir pressure at any time. Then you know the initial, you know the, this is the reservoir pressure after a particular period of time. Then this is the average reservoir pressure, which is now the pressure at time 0 plus the pressure at any given point in time divided by 2. So you now see that from there they can calculate the maximum water influx. This is the formula of calculating the maximum water influx, and from there theta is the encroachment angle, the angle that this particular water is getting into the reservoir. Is it at 90 degrees, is it at 60 degrees, 70 degrees, and all of that. So they have to also note the encroachment angle. So if we get now to our MBAL, our water influx, we would like to take any model. I will just look at what I have discussed. So I will take the Felkovich. And then from there now you should be able to know which type of aquifer we have. Generally our reservoir could be radial in shape, so we also have to assume that the aquifer also is radial in shape. That is, aquifer also is radial in shape. So from there now we have now to input these parameters. We have our reservoir thickness, let's say it could be around 80 feet. Our reservoir radius in feet, let's just say 150 feet. We have our inner radius ratio, the outer slash the inner radius. Then we have our encroachment angle, let's say it's 180 degrees. Then we have our aquifer parameter. So what I will do, let's cross check from here and use these values, because we'll be doing a history match, and doing the history match, all of these things are very important. Anyway, when we get to history match, we'll work on it. So this, we could say 100 permeability, millidarcy permeability, that's the permeability of our aquifer. So this is the model that we are going to use to simulate the behavior of the aquifer as production is taking place. We'll go now to next. Our rock compressibility, we'll just leave that from correlation, but if you have a particular value for it, you could also input it. We have our rock compaction. So you may have your rock compaction. So the rate at which the rock is compacting as you're doing production, if you have the data, you can also input it there, but it's not a must. Then we have our not pore volume, our relative permeability. So from here now we could also get our relative permeability. There are different ways of obtaining the relative permeability. If you come here, we could have maybe tables. Maybe you have probably carried out the experiment in the lab based on the water saturation levels, and they have measured the relative permeability of water, of oil, and of gas. So in that case, you have to input your parameters here, because the relative permeability data is very important for us to know how the fluid can easily flow, because the presence of one fluid within the reservoir hinders the others from flowing. So you need to be able to model that situation to know how easily the fluid can flow. But in this case, may use a correlation. We call that the Corey functions that we can use to model the relative permeability of our reservoir. So we'll go to, I have a PowerPoint here, I think I illustrated. Okay, so this our relative permeability, and this is our function that is used. Their function, we have KRX, which is the relative permeability of whatever substance you're talking about. It may be oil, it may be water, and all of that. Then we have our XF, our XX, which is our phase saturation. We have the phase residual saturation, and then we have, so if this is water, we'll be talking of water, irreducible water saturation. Then here is a maximum phase saturation. Then nx, which is what we have there, is what we call the Corey exponent. So most of these parameters are measured in the lab. They are measured in the lab. So we'll go back to our MBAL. We look at what we have here for Corey. Okay, so this is the parameter I have here. Let me, I hope copy and paste will go, because MBAL the steps when it comes to that. Paste. Okay, this one has gone easily. So you can easily input all of these parameters. Then the software will use these parameters now. We have our residual saturation, we have our endpoint, and we have our exponent. Once you input these parameters, the software will use these parameters now to do the calculation of the relative permeability of water, oil, and gas. I said most of these parameters are measured in the lab. So we go now ahead. What we need now here is our production history. You need to know at least for the past time what has been the production of that particular reservoir, because our interest here is to analyze the reservoir and see how we can do prediction of the reservoir. If the reservoir energy is not sufficient enough to drive the oil, what can we do? Maybe we can carry out 1D model of water flooding, gas injection, steam injection, and all of that. So what we are going to do here now is to input our production history. So I'll come to the production history and I copy all of this. Copy. Then I come here, I click, and I paste. Now we have our production history here. We have our reservoir pressure. We have our cumulative oil production, our cumulative gas production, cumulative water, and cumulative water production. If we have some injection, maybe some injection has taken place for a period of time, maybe gas injection, we have to input that parameter, and maybe water injection also we input the parameter. From there now we'll click on validate. Once it turns dark like that, it means it has been validated. Alright, we can go to our plot up there to look at the performance of the reservoir from the production that we have inputted. What is the performance of that reservoir? So you look at it from here, you can see the reservoir pressure, what's happening with the reservoir pressure, what's happening with the cumulative oil production. I could also put cumulative gas production. Okay, maybe maximum 2 plot. Alright, so we'll leave it like that. Alright, so you see all of these parameters are parameters. This is just what you have inputted into the software. It's nothing else. The production data that you have inputted into the software, what we have done here, that's just the production there. It's not as if you have done anything. So don't look at this and say this is production prediction. You have not done any production. You are just plotting the history data that you have inputted into the software. All right. Now, okay. Some parameters. Let's be sure that everything is okay. Oh, all right. Is that 0.23? 0.23. All right. Now, the next thing we have to do now is to do what we call history matching. We all know that the world has been taken over by what we call machine learning. Machine learning is just an aspect of teaching the machine on how to carry out a particular task. Then you allow that machine, and that machine is able to carry that same task over and over. Like most of what the social media is using is machine learning. Now what the machine does is, immediately you get into a system like Facebook, whatever you're searching, whatever you pay attention on to watch, this machine is actually noting exactly what you as a person like. When you go there, what are the type of pictures that you see, what are the type of videos that you watch. The machine knows exactly that, okay, this particular person, you like this particular type of video. So anytime you get into Facebook, what the machine does now is bring out these pictures and videos close to you, so that what you will now do is to pay attention more on them, and at the end of the day, the investors are making money, because the more you watch, the more money they make. The more time you spend on Facebook, the more money they make. So their job is just to make sure that you stay on Facebook no matter what. There is this movie called Social Dilemma that is probably acted by most of the first guys who were those who initiated this machine learning aspect into social media. If you get into Social Dilemma, you understand it, what I'm explaining better. So the same thing is happening in our reservoir system. We have inputted our parameters. The machine now, this software that we have, the MBAL, is able to give us a prediction about how that reservoir is supposed to perform. But rest assured that this prediction, this simulation that the system is bringing out will definitely not match with our history data. It's just like someone builds up a robot. You build up a robot and you have to teach that robot how to carry out daily activities. So what the system has done now is to bring out a model, but you have not yet taught that model on how to carry out the activities. So the process now of teaching that model how to carry out the activities now is what we call history matching. So what we are trying to do is to make sure that the simulation that we have matches with our production. So if the simulation matches with our production, we are 100% sure that if we allow that simulation to do further prediction into the future, it will give us good values about the performance of the reservoir. That is what history matching is all about in very simple terms. in very simple terms. I'm not here to be bringing you textbook definitions that will confuse your brain. I'm trying to put it in a very simple term. You build up a model, and then you now have to teach that model how to carry out activities. Then you allow the model now to carry out further activities. So the process of teaching that model in MBAL now is just like making sure that this model matches with our production data. Once it matches with our production data, we know that this model now can do further prediction for us. So we'll do a little bit of history matching. I'll come here under history matching. The first thing we'll look at under history matching is our energy plot, to see what are the main sources of energy within that reservoir. So look at our energy plot. We realize that within that reservoir it is basically fluid expansion and pore expansion, PV expansion. You remember the various sources of energy in the reservoir that we have talked about. We have rock and fluid expansion, we have gas cap expansion, we have solution gas, we have water influx, and then we have the gravity. Those are the various sources of energy within the reservoir. Most of these energy sources depends mostly on an analysis of this production history. It depends on an analysis of this production history. But remember vividly, when I gave the material balance equation, I gave the various parts of that equation that is influenced by each of these energy sources. That means you should be able to know that this particular component of the material balance equation, I don't know if I have it here. Alright, so these are the various components that I ended up giving for the material balance equation. I think it was this plus this plus this plus this is equal to 1. And I now said each of these represents different energy sources within the reservoir. We have our DZI, depletion drive index, we have water drive index, we have segregation drive index, and then we have expansion drive index. So all of these added together equal to 1 forms the material balance equation. So from our production history, the system is able to tell us exactly what the energy of the reservoir has been over the past production. So there are two types of matching, history matching. What we have is analytical history matching and graphical history matching. We are going to start with analytical history matching. Alright, so what we have here, this is our production data. This is our production data, and then this our simulation. Our simulation without aquifer influx. But I think we indicated that we have one aquifer influx here. Alright, done. So we'll go now. So if you look at what we have here, you have history matching and you have production prediction. So it is after our history matching that we can now go ahead to carry out our production prediction, because it is not longer our past history that is doing the prediction for us, but it is the robot that we have produced. In this case, we are talking of simulation. It is that simulation that is going to do the prediction for us. But for us to have an accurate robot that can do the prediction for us, we have to carry out history matching. So under history matching, we have our energy plot. Then we have talked about analytical method and graphical method. So we have a little bit of history here before we can go to our MBAL to do the analysis. Now, within the reservoir, there are certain parameters that you carry them out and you are so sure of them. So we can always recall that some of these parameters will always come with uncertainty. So what you have to do now is, if the simulation is not matching with the production data, it simply means that there are some data that have a lot of uncertainty in them. So what we will do now is we will choose these parameters that we don't really trust. There are some parameters that you may have trusted. I mean, in the life of the world, they have measured them. The engineers at the field, they know exactly how they carried out this data. So they can easily trust some, and some they will not trust that much. They will now say, okay, maybe this permeability value is not exactly this. It could vary between this and this. So what we will do now is, we will select those parameters that we don't trust, then we give a limit for them, then we allow the software now to work within this interval and try to find the right value that will enable this our simulation to match with our production. So we have some parameters. We are not choosing all of them. We choose only those parameters that we don't really trust that much. Those parameters that we don't trust, we allow the system to do a regression analysis on these parameters that we have chosen within some defined limit, and within that limit, they are going to now pick the value of that parameter that will shift the simulation closer to the production value, to the production point, because our end point is to ensure that this our simulation matches with the production data. That one is what we call analytical history matching. So for graphical history matching, it comes in more or less to confirm what we have under analytical history matching. So what this tells us is, we have a series of plots that we can look at this series of plots to look at how these plots also have matched with the history data. If we realize that there is some kind of a good match between them, then it simply confirms to the fact that the analytical matching that we did is okay. If we go to the graphical method and we look at the graphs and we see that there are some adjustment that needs to be made, once we do the adjustment, the analytical history match will automatically readjust. So we need to come back to the analytical history match and try to see how we can still readjust it again, because in the course of adjusting this one, we may have realized that the simulation now has shifted away from our production data. We need to go back to analytical history match and make sure that they matches. If they don't match, until they match before we can stop. So that is the reason why artificial intelligence have become so widely used now in the oil industry, because there are some reservoirs where using these computer assisted softwares to do history match is so difficult and so complicated, if not impossible. So what they have done now is to develop some artificial intelligence system that they can easily use now to ease their work and do some of this history matching. All right, so what you will do now is, since we are running out of time, or about 50 minutes. All right, so what you do now is you just try to input. Please, I'll send the PVT data before tomorrow. I expect that you must have done PVT matching here. PVT matching, you come to match, you input the data here, then you go now to match, then you have to now go to plot. After match, you go to plot, so that you can plot the match data with the laboratory data, so that you should be able to see which one is a match. Then you can also go to parameters to see which of them is having the best parameters, as we explained. That's the reason why, because of the lack of this PVT data, that's the reason why we go to our analytical plot. We are seeing only without aquifer influx. We need to have with aquifer influx. So if we don't have that PVT matching, we will not have that one. Because since our reservoir is having an aquifer, our interest is not matching this one, because this is the simulation of without aquifer. But we need the simulation of with aquifer, so that our interest now will be matching this our data with the simulation data of with aquifer. So that's what you have to go and do, so that tomorrow when we come, we just do our history match, then we do prediction. There are two ways in which we are going to do our prediction. We can predict, we can just do a rough prediction without a well model, or we can do an accurate prediction with a well model. Remember, for you to predict the performance of a reservoir, it doesn't depend only on the reservoir. The reservoir can perform well, but our wellbore does not perform. That is the reason why nodal analysis in quotes is coming in, which we have already talked about a lot during this internship. We have talked about nodal analysis. So the reservoir could perform well, but we need to know how the wellbore also is performing, so that we should be able to do an accurate prediction. So we could just do a rough prediction without the wellbore model, and we will also do an accurate prediction with the wellbore model. So what you have to do now is to go through this and make sure that you do the history, the PVT matching, so that by tomorrow we will now continue from there. So if you have any question, you can ask your question.